Hello everyone, this is Nagasai Maitreya and today I am going to solve overhanging beam using Macaulay's method. Now this is the problem given. Here as you can see there is a UDL acting over here between B and C, and at A we have a point load acting downward, and at E we have a point load acting downward, and we are given the cross section. So first we need to find the moment of inertia of this cross section, and then we are going to solve this beam using Macaulay's method. Note that here the Young's modulus of the beam is given as 200 gigapascal. Okay, so the things we need to find are the deflection at point E, the slope at A, the maximum deflection in the beam. Now let's first calculate the moment of inertia for the overhanging beam which was given to us. So these are the dimensions of the beam. This is 200 mm and this length is 12.5 mm. This length is 150 mm and this is 12.5 mm. We have to note that the values of the length is in mm. Now here first to find the centroid of the entire T section, now we are going to find the centroid of this first one. So the centroid will be at the midpoint of this rectangle, that is 150 by 2. Why we are taking 150 by 2 is because it is symmetrical about y-axis. So and the area of this beam is 12.5 into 150 mm square, that is 1875 mm square. Now the centroid of the second one is 150 plus 12.5 by 2, that gives 156.25 mm, and the area of this part is 200 into 12.5 mm, which gives 2500 mm square. Now for the centroid of this T section we will use the formula, that is y bar, that is the centroid of the T section, that is equals to y1 a1 plus y2 a2 by a1 plus a2, where y1 is the centroid of the first part and a1 is the area of first part, and y2 is a centroid of the second part and a2 is the area of the second part. Now uh, when we substitute the values we will get the centroid of the T section as 121.428 mm. Now we have to find the moment of inertia of the T section. We are going to use the formula I is equals to BD cube by 12 plus AH square, where H is the difference between the centroid of the T section and centroid of each section. So here H1 is equals to the centroid of the T section minus the centroid of the first section, that gives 46.428 mm, and H2 is the difference between the centroid of the T section and the centroid of the second section, that gives 156.25 minus 121.428, that is equals to 34.822 mm. Now substituting the values of H, A, B and D in the moment of inertia equation, we get the moment of inertia as 1062127.9.76 mm power 4, that is equals to 0.01062 into 10 power minus 3 meter power 4. Now as we have calculated the moment of inertia of the T section, now we are going to solve the beam using Macaulay's method. We are given the value of y as 5 and x as 10 and z as 10. A is 1.5, B is 3 and C is equals to 2. As you can see, these are the values that are given to us. X is 10, Y is 5, Z is 10 and 1.5 as A, 3 as B and 2 as C. The length of A, B, C are in meters and the forces acting are in kilonewtons. First we are going to find the reactions at B and D. Now in the beam, as we can see here, it is 10 kilonewtons and here it is 10 kilonewtons, and now we are going to convert this UDL into point load, that is y into the distance, that is y into C is y is 5 kilonewtons per meter and C is 2 meters, that gives 5 into 2, 10 kilonewtons per meter, 10 kilonewtons. That is the point load acting at a distance of 1 from B. As you can see, now RA plus RD gives rise to 10 plus 10 plus 10, that is 30 kilonewton. And to find RB and RD, we are going to find the moment at B and D. Now the moment at B and moment at D will be 0. As we are taking the moment at B, the moment at B will be 0, and while taking at D, the moment at D will be 0. For moment at B, and taking the clockwise direction as positive and anti-clockwise direction as negative, at B 10 kilonewton is acting in anti-clockwise direction, so that is negative, plus the distance between this force and B is C by 2, that is 2 by 2 by 2, that gives 1 into 10, and it's acting in clockwise direction. Now similarly, while writing down the equation and solving it, we get RD is equals to 13.33 kilonewtons. And likewise, if we calculate the moment at D, we will get the RB value as 16.67 kilonewtons. We can also get the RB value by substituting RD value in this equation. Now as we found out the reactions at B and D, so this is basically the Macaulay's method. We are going to pass a section uh, in the final segment of the Macaulay beam, of the overhanging beam. So it is at an x distance from A, and it is passing to the final segment. And in case of Macaulay method, we are gonna extend the UDL and add a UDL in the opposite direction to maintain equilibrium. Now here, from Macaulay method, we are gonna write the bending moment equation. As we have seen in the previous slide, the forces acting, here the moment equation will give you this. These are known as Macaulay bracket, and we have written the equation. Now as we know, the bending moment is equals to EI d square by dx square, d square y by dx square, where E is Young's modulus and I is moment of inertia. Now integrating on both sides, we will give the equation for dy by dx and y, where y is deflection and dy by dx is slope. Now using this equation, we are going to find the slope at A, and using this equation, we are going to find the deflection at E. As we integrated the bending moment equation, we will get two constants, C1 and C2. For finding the values of C1 and C2, we are going to apply the boundary conditions, which are at x is equals to 1.5 and x is equals to 4.5, that is at B and at D. This is because at these points the slope will be 0. Now substituting the values of x is equals to 1.5 and y is equals to 0 in the equation, we get C1 of 1.5 plus C2 is equals to 5625, and x is equals to 4.5 and y is equals to 0 gives C1 of 4.5 plus C2 is equals to 93526.67. Solving these two equations will give C1 value and C2 value. As we got the C1 and C2 value, now we are going to find the deflection at E. At E, the length of the beam is 1.5. Since the beam is like this is A, and then B, and then A plus B, 2A plus B, that is equals to 2 into A is 1.5 plus B is 3. That gives rise to 3 plus 3, that is equals to 6, which is E. This is A and this is E. So at E, x is equals to 6. Now substituting the value of x is equals to 6, and since we are finding deflection, we are going to use the equation for EIY. Here, substituting the value, we will get the y as minus 12.26 mm. And the next part, the slope at A. For point A, the x is 0 since it is at the starting. A, E, it is 0, and we are calculating x value here. The x will be 0 at A. So if we substitute x is equals to 0, and since we are finding slope, we are going to use ei dy by dx. Since every value will go to 0, we will have left with the constant c1. So then dy by dx is equals to, the c1 value is 29300.56. dy by dx will give us the slope at A, and this is how we find the slope at A. Now we found the deflection at E and the slope at A. Thank you.